All right, we're back. We're going to find some integration today again, section 4.6, but we're going to go into the natural log. So some of our answers are going to be in natural log forms. We're going to be able to take the natural log or the integration of a natural log, and then we're also going to look at some problems where we may use some long division. So I don't have a lot of examples, just kind of running through some different things and some things that you may find along the way. The long division problem is kind of neat to look at. I don't necessarily think that you're going to run into it very often as we do problems with integration. With that being said, example 1 here, we have the integration of 2x over x minus 1 squared. So what can we do with this? Well, I see a u coming into play being that quantity to the exponent, kind of as a unwritten rule where we're going to start. And it may not work out, but we may see that this u has to be changed later on. Let's try it and see what happens. So our du then is going to be dx, isn't it? So that takes care of the dx. So I'm looking then at the integration of 2x over u squared du. Well, that's kind of a problem. So what I need to do is get rid of this x, and the way I can do that is solve for x, and I end up with a u plus 1. So we have the integration then of 2u plus 2 over u squared du. Or I could have brought that 2 out. I guess I normally bring the 2 out, don't I? But this time I multiplied it in. Well, now what can we do? I still don't have this in a form that I can really integrate yet because I have u's in the numerator and denominator. So what I'm going to do is go ahead and break this up. And I'm going to have 2u over u squared plus 2 over u squared du. What that's going to allow me to do is simplify this to 2 over u. And since I have a single variable in the denominator, that rings a bell to me. And then I'm going to bring this u squared to the numerator as a negative exponent. So if I think about 2 over u, remember that rung a bell with me. Ding, 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 ding. And we have 2 natural logs of the absolute value of u. Integration of 2u to the negative second. We're going to increase that exponent by 1. We get negative 1 divided by negative 1. So we're going to get negative 2u to the negative first plus c. Replacing our u with x minus 1, we have 2 natural logs of the absolute value of x minus 1 minus 2 over, because I can bring that to the bottom again, of x minus 1 plus c. I will caution you, I see this almost every year. Be careful, be careful, be careful, be careful. I can't say it enough. A lot of people, once they integrate this to 2 over 2u to the negative first, they say, I know that. That's a natural log. And they'll actually change this to a natural log as well. That would negate both of these, and you'd end up with 0. So be very careful that you don't try to double integrate this. Okay, because if you integrate this, we'd have to also integrate this for the second time. And we don't do that because it doesn't tell us to double integrate. We have a one simple integration rule, or integration symbol. All right. In our next example, we have the integration of x squared plus x plus 1 over x squared plus 1 dx. So if I think about it, I'm going to let my u be x squared plus 1, wouldn't I? That makes sense. That's my denominator. That's what we've done in the past. So du would equal 2x dx. Well, if I look at my numerator, that doesn't quite work for me, does it? We really don't have a whole lot there to work with. If we were to do, we could divide maybe this 2x over, since we don't have an x in there, but it gets very complicated once we don't have that nice clean integration or substitution in this case. So what we can do is go ahead and do a long division with this. And again, this is something that it's kind of neat to see. I don't necessarily know how common it is to run into. So if we have x squared plus 1, it's going to go into x squared one time, isn't it? So we have 1 times our x squared plus 1, we get x squared plus 1. We're going to change those signs, and we end up with x. So I can break this up. I have the integration of 1 dx plus the integration So what is my leftover? My leftover is x, or my remainder is x. So I can write this as 1 plus x divided by x squared plus 1. A little bit of pre-calculus and algebra 2 there, huh? So we have plus the integration of x over x squared plus 1 dx. I know this. I'm going to leave it. I'm going to go ahead and play with this here. So if you remember, I let u equal x squared plus 1 up here, and du equal 2x dx. Well, look at that. I have an x dx, and there's my x squared plus 1. So I can keep my integration of 1 dx. I know that again. Here, I have to get rid of that 2, so I have a half du equals x dx. So I'm going to over here have 1/2 the integration of my x dx again is going away, so it becomes my 1 over u du. So be careful with that, or make sure you understand where everything went there. So that x dx here went to this 1/2 du, since we have that as our substitution. Our x squared plus 1 in our denominator was our u, so that's where we got our 1 over u. So now I know the integration of 1. Remember, that was x. And if you want a plus c. The integration of 1 over u, well, that's the natural log of the absolute value of u plus c. I'm going to replace my u with x squared plus 1. And we also have this c plus c. So again, a constant plus a constant gives us, a constant. So we have x plus 1/2 the natural log of the absolute value of x squared plus x plus 1 plus c. And here's our answer. And then the last one, we're actually going to have a natural log within our problem. So a couple things that I would like for you to see with this. One, that exponent of 3. Anytime we have the natural log of a variable to an exponent, or something to an exponent, we can bring that exponent to the front of our natural log. So we can write that as 1 over 3x natural logs of x dx. And that's going to make our life a lot easier if we bring that exponent to the front. Now that's going to be miserably difficult if we don't, but it makes our life a little easier. So I can bring that 1/3 outside as well as our 1/3. So we have 1/3 the integration of 1 over x natural log of x. Since our x's are all in our denominator, that is kind of an ugly thing. I could let u equal that entire denominator, which then we'd have a product rule, which we normally at this point in time are not going to see a product rule occurring. We could also let u equal x. Well, if u equals x, that's just going to be a single variable for a single variable. That will never happen for us. Or we can let u equal the natural log of x. I know something about the natural log of x, and its derivative. Derivative of the natural log of x is, 1 over x dx. That's what we have. We have a 1 over x dx, don't we? So we have 1/3 the integration of 1 over u du. And the integration of 1 over u is the natural log of the absolute value of u plus c. Replace your u with the natural log of x. It becomes kind of fun there. So we get 1/3 the natural log of the absolute value of the natural log of x plus c. So we actually end up with a natural log of a natural log. So that gives you an idea of where we're going to see some natural logs occurring, whether they occur after we integrate or before we integrate and we let our u be that natural log. Normally, if you have an integration of a natural log with something of some sorts, you're normally going to see that 1 over x come up, and that natural log being what our u is going to be. So just a couple things to look for. Again, we've looked at exponentials where we let we let the u be our exponent, and we've looked at quantities where our u is the quantities. Now we're seeing where u can be the natural log of x, or natural log of a single variable. So there's several examples. If you have questions, please let me know. Good luck, enjoy, and of course, happy integrating.